All right, well, good morning. This short video is a little bit about um, heat exchangers, a little bit more. In short, what I'm going to ask you to do on Monday is primarily figure out heat exchanger U, overall heat transfer coefficient, or overall thermal conductance. And that really is easy enough. We covered that in lecture. I'm going to, in addition though, put a little bit about area. And so this video is to discuss how you do those calculations. It's all pretty straightforward. I alluded to it on the homework sheet, but if you would be interested in getting some guidance, this video will help. So, in short, when you have heat exchangers, probably the two main questions we have is, hey, for a heat exchanger that we're thinking about, what's the U and what's the area? So, the simplest type of heat exchanger would be a flat plate heat exchanger. So just imagine this is a sheet of metal, and we got a situation where we want to exchange heat between two fluids, two flowing fluids. So a good example would be we want to cool down engine oil with water. So what we want to do is separate those. We don't want the water and the oil to mix. So we could have this oil come in here like this. There would be a opening here and a passageway for the oil to go through, and then we could have the water flowing on the bottom, and then heat would transfer down from the oil to the water. And that way we get exactly what we want. We get heat transfer, but at the same time we don't get the fluids to mix. All right, so easy enough to figure out the U. We talked about that last time. I'll review it really quickly. But what about the area? How big do we need to make this plate given that we want a certain amount of heat transfer? And the example I'm going to do, let's say we want 40,000 watts. We got this oil coming in and we want to get 40,000 watts out of it so it comes out at a cooler temperature. 40,000 watts heat transfer. What area do we need? Okay, and that's a really fundamental question that you might get involved in design if you're doing stuff with heat exchangers. All right, well, let's get at it. First thing, a little bit on heat exchanger geometry. There's all sorts of geometries. I encourage you to look in the book. I give you some figures to look at. But in short, what we're going to have, the simplest geometry is we're going to have a flat plate. So that represents that plate. Okay, and we're going to have two fluids, and so you can think about there being 4 ports. 1, 2, 3, 4. Okay, and what you're going to do is you're going to have some sort of hot fluid go through one passage right here. Okay, and so maybe that could be like our engine oil. All right, and then you're going to have a cold fluid go through the other passage. Now that cold fluid could go either way. It could go from left to right or right to left, and that's a really interesting question. What's better and how does that work? On the homework, I ask you to look at it a little bit. If it goes this way, if this was our water, that would be called parallel flow. The fluids are going in the same direction. On the other hand, if we had the water go the other way, that would be counterflow. So parallel flow, same way, counterflow, the opposite way. All right, so that's our simplest geometry, and two main questions then. For this plate, okay, what is the U? Okay, and then given we want a certain amount of heat transfer, what area is required? All right, so a quick reminder on the U, or a quick reminder on the U. Okay, earlier in the semester, we started our basic idea of heat transfer, say going from one fluid to another. Okay, and we modeled it this way. We used this basic idea that flux is delta T over unit resistance. Okay, and if you need a reminder on that, what you can do is just go back to test 1 and take a look at the problem on heat going through a skylight. We actually had heat transferring through a skylight, and I asked you to figure out the resistance and therefore the flux, and it's the exact same thing for heat exchangers. So that'll give you a good review on that. Okay. Many times in heat transfer, this is written a different way, in a similar but different way. So this is saying that the heat transfer is driven by the delta T and resisted by the resistance. Simple enough. Or we can say that the heat transfer is driven by the delta T, okay, and it is allowed through by a certain thermal conductance, okay, overall thermal conductance U. Just really similar ideas put a different way. And you can see from the algebra, or just from the nature of those equations, that our U is 1 over our unit resistance. Okay, so that in short is what I'm going to ask you to do at a minimum on test 3, is to, for a physical situation, calculate the unit resistance and then do 1 divided by the unit resistance and get the U. Okay, in addition, so that may be, say, like if the problem's worth 10 points, that's going to be worth 7 out of 10 points. And then I would like to give you I would like to see you get a stab at getting the area. So how do you go about getting the area? All right. Well, so taking off from there, we can come up with what the equation is going to look like. All right. Taking a look at this equation right here, we know flux is heat transfer per unit area. So flux would be heat transfer per unit area. And our goal is to have an equation which has U for a heat exchanger and area in there. So I could just write it like this, and we're almost to our basic equation. Q, okay, over A is equal to U times delta T. Okay? All right, but as you'll notice in the book, it's written in a linear fashion, so I'm just going to move the A to the other side. So the heat transfer for a heat exchanger is equal to the U for the heat exchanger times the area through which the heat gets transferred times the difference in temperature between the two fluids. So this might be the hot fluid, and this might be the cool fluid, and that is it. We're almost there. Okay, so there's our heat exchanger equation, and that's going to allow us to figure out A once we have U. But give me just a second to get another drawing up there, and we'll talk a little bit about how we're going to get the temperature difference between the two fluids. So in short, while I'm erasing, it's that same issue that you've had on homework number 10 and homework number 11, that the difference in fluid temperatures is changing. So I'm going to draw a quick heat exchanger, and I'm going to get some temperatures up there, and I'd just like you to think about it for a second. Hopefully you have a calculator, okay, and can take a guess at how we're going to do this. So I'm drawing a simple flat plate heat exchanger, like is talked about in homework number 12, and I'm going to have a hot fluid going through there. And I got a cold fluid going there, through there. And I'm almost got this done, so just hang in there for just a second. All right, so there we go. So there's the issue at hand. Let's say that we're trying to use this equation. Q is equal to U to the heat exchanger, A times delta T. What delta T stands for the temperature difference between the hot fluid and the cold fluid, and what delta T are we going to use? Okay, well, if you take a look at the hot fluid, delta T doesn't stand for temperature difference in the fluid. In this case, it's negative 40. Delta T stands for the temperature difference between the hot fluid and the cold fluid. So heat's going transferring this way. Actually, I'm sorry. Yeah, that's fine. I'm gonna go with 36. Heat's transferring that way, and if you take a look over here, the delta T is 65, and over here the delta T is 4. So what delta T are we going to use? All right, and you could guess at it and say, hey, I'm going to use the average delta T between this 65 and this 4. And if you did that, 65 plus 4 is 69 divided by 2 is 34.5. You get a average delta T of 34.5 degrees Celsius. Okay, by the way, all these are in Celsius. Once again, though, there's this problem that the heat transfer is large at first, so the delta T falls off quickly, and so this is going to be an overestimate of the delta T. So we use the same idea we had earlier in the semester, where if we have a delta T for fluids that is changing, we're going to use the log mean temperature difference. So that is our second formula for heat exchangers, and let me get that up there for you. So log mean temperature difference for heat exchangers. And then we'll pull out our calculator and see how it works out. Let's make sure I write it the same as the book. Yep. Okay, so log mean temperature difference, very, very similar. Delta T minus delta T over natural log of a ratio of delta T's. Okay, for flat plate heat exchangers, you can think of delta T2 as the delta T on side 2, okay, and delta T1 as the delta T on side 1. So you can think of there being a side 1 and side 2, and it doesn't matter which one you label as side 2 and side 1, you're going to get the right answer. So that is the last equation that you need for heat exchangers. Let's just see how it carries out. Let's work out the delta T, the log mean temperature difference. Keeping in mind earlier that I said, look, it looks like it's about actually, I'm sorry, I did that math wrong earlier. A delta T here of 65 for, no, actually that's right, 34.5. That was our earlier guess based on the average of this number and this number. Okay, we'll just plug and chug. So delta T on side 2 is 4. Delta T on side 1, 65. Okay, and then we have to just make sure we do it in the same order, ln 4 over 65. Okay, and let's see what temperature difference we actually end up getting. So I'm going to pull that on my calculator, just really work out that really quickly. Okay, and the delta T we get is 21.9 degrees when I do it that way. 21.9 degrees C. So what that number is saying, this 21.9 degrees C, is saying, hey, the delta T for purposes of heat transfer on average is about 22 degrees C. It's really big over here, but that delta T falls off quickly, okay, and then later on it's smaller. All right, I am going to leave that number up here. I'm going to do a little bit of erasing and take a look at a typical problem. And that should put you in pretty good stead for trying that example, that problem on homework number 12. And then in addition, if you want to go on the test 3, you want to go beyond just getting the U and also doing some problem solving that would be typical of what you do out in industry. You'll be able to handle it. Okay. All right, give me just a second here. Okay, so let's say we got a situation where we have some fluid and we're cooling it down and we want to remove 40,000 watts. That's the heat transfer we want. So we're getting 40,000 watts out of this fluid, and it is going through this heat exchanger surface. It's going through this heat exchanger surface. What area does this need to be? And of course, that's a big question. You know, a lot of times the materials that are used for heat exchangers are expensive, and you want that area to be as small as possible so that you're not spending as much money. Okay, well, just taking a look at our basic equation for heat exchangers, Q UA delta T log mean. I gave you the Q. We're trying to transfer 40,000 watts. Okay. The U would be something you figure out by doing 1 over the resistance. So in this case, I got a really large U. That may seem a little hard to get your mind around, but many times this is highly conductive material. And if this flow is turbulent and that flow is turbulent, we get great U values. And then finally, delta T log mean, well, that's that 21.9 degrees C. So we have everything we need in that equation to solve for A. I'm going to show the work down here really quickly. Try it yourself and see if you come up with a reasonable area. So a little bit of work time. Actually, if you could make a change, that U, I'm sorry, I added an extra 0. Sorry about that. 1,000 would be a really good U. Wow, 10,000, that would be something else. So please change that U to 1,000. Okay, so looking at that calculation, my calculator, when I changed the U to back to 1,000, back the U to 1,000, gave me 1.83. And what about units? Okay, 40,000 watts. Take a look at the denominator. 1,000 watts per meter squared of heat transfer per degree C temperature difference between the two fluids times 21.9. So that's going to be around 21,900 watts heat transfer per meter squared of surface. And so watts over watts per meter squared is going to give us meters squared. So that works out perfectly. So that tells us, hey, if we're going to use this strategy for transferring heat out of the fluid that we're trying to cool, we need 1.83 meters squared. And that's pretty large. Okay, but if you take a look at some heat exchangers, they have some very clever ways of getting a lot of area in a small package. And if you go on and do work in engineering with heat exchangers, you'll see some of that. And of course, there are some nice images in the chapter on heat exchangers for you guys to look at. Okay, so for heat exchangers, we have this basic equation. You know for a flat plate heat exchanger how to get U. Given you also know how to do delta T log mean, the remaining question is, hey, what about this number here? How did I come up with 40,000 watts? And that's a really nice thing about doing this topic last in the semester is it brings together stuff that you already know, and you can do what seems like some very complicated problem solving with just some basic equations. So very last thing, how are we going to figure out Q for a heat exchanger? So give me just a second to get an image up there, how to determine Q, and that will do it for today. Okay, so let's just take a look at one of the two fluids, okay? Let's say it has a certain mass flow rate, okay? And we're taking it from an inlet temperature to an outlet temperature. How much heat would be, let's say that that's being cooled, how much heat would be being transferred out of that? Okay, well, that's our most basic equation from homework number 9 and probably homework number 10 and homework number 11, that if you want to get the heat transfer for a fluid that doesn't change phase, you take its mass flow rate, you take its specific heat, and you multiply it by delta T. Okay? And so in the problems that you're going to take a look at, you'll have this information, be able to work it out. And of course, if you're doing something like cooling off engine oil, you're going to know the mass flow rate of the engine oil. You're going to know how much you want to cool it off, and you can look up the specific heat, and so you can get the Q for that fluid. Okay? How about the Q for the other fluid? Let's say the cool fluid that's going through on the other side. Okay, well, if that fluid doesn't change phase, the same equation applies. The same equation applies. But there's one more idea to throw in there, okay? If you think about it, we have Q, or heat transfer, for one fluid, okay, and we have heat transfer for another fluid. Well, the heat that comes out of this fluid goes to that fluid, so those two Q's need to be the same. Finally, we have our Q equals UA delta T log mean, and that's the heat transfer that actually gets through this plate. How does that compare to the heat transfer that gets out of, say, like this engine oil or this fluid? Well, if this heat exchanger is pretty well insulated, and you can assume that for all the problems that we do, and of course it's not a bad idea if you're using heat exchangers to insulate them, then the heat that gets out of this fluid will be the heat that goes through this surface, which will be the heat that goes into the other liquid, so all three Q's are the same. Q equals m dot Cp delta T for the hot fluid, Q equals UA delta T log mean for the plate, and Q equals m dot Cp times delta T for the cold fluid. So, brings together a lot of stuff that you studied during the semester. Make sure that you're good to go on calculating U for a heat exchanger from one fluid to another, and then after that, give it a stab to try to work out, hey, what area would be required, and that'll ask you to use those equations for that equation, m dot Cp times delta T, and also think about the log mean temperature difference for a heat exchanger. All right, hey, please email me if you have any questions as you're getting ready for test 3, and we will see you guys on Monday.